Good evening, ladies and gentlemen, boys and girls. My name's Alan Willison, and it's my pleasure and privilege to welcome you to this meeting of the Hertford Astronomy Group. I can see that we've got quite a few new people with us tonight, both in the university and in Zoom. So please, anyone who is new, don't go away without having said hello to myself or to members of the team down in the university. We are a very friendly bunch and we want you to go away with very positive experiences. The format of the evening is a little bit different to our usual one. Because we're starting later, Martin has suggested that we don't have his section about the forthcoming night sky. So after my introduction, we'll move straight over to Jerry, who will introduce tonight's speaker. After the talk, there will be an opportunity for you to ask questions. Those of you at the university, you can ask them directly. Those of you on Zoom, if you could submit your questions via the chat facility, they will get read out so that we can all share them with us. For those of you at the university, we hope you like the room you're in, a different one to our usual one, but quite nice and cozy. And we ask you, as usual, please, if you've got a mobile phone, could you just check it's set to silent, off, or whatever, just so that it doesn't go off in the middle of the meeting. For those of you on Zoom, could you please make sure that you stay muted? Be careful of the space bar on your computers, because that does have the knack of putting your microphones back on. So just make sure you stay muted and you'll enjoy the show. So that's my short and sweet introduction. I'm now going to pass over to Jerry, who's going to introduce tonight's speaker. So Jerry, if you're ready, over to you. Possibly. Good evening, ladies and gentlemen, boys and girls. My name's Alan Willison, and it's my pleasure and privilege to welcome you to this meeting of the Hertford Astronomy Group. I can see that we've got quite a few new people with us tonight, both in the university and in Zoom. So please, anyone who is new, don't go away without having said hello to myself or to members of the team down in the university. We are a very friendly bunch and we want you to go away with very positive experiences. The format of the evening is a little bit different to our usual one. Because we're starting later, Martin has suggested that we don't have his section about the forthcoming night sky. So after my introduction, we'll move straight over to Jerry, who will introduce tonight's speaker. After the talk, there will be an opportunity for you to ask questions. Those of you at the university, you can ask them directly. Those of you on Zoom, if you could submit your questions via the chat facility, they will get read out so that we can all share them with us. For those of you at the university, we hope you like the room you're in, a different one to our usual one, but quite nice and cozy. And we ask you, as usual, please, if you've got a mobile phone, could you just check it's set to silent, off, or whatever, just so that it doesn't go off in the middle of the meeting. For those of you on Zoom, could you please make sure that you stay muted? Be careful of the space bar on your computers, because that does have the knack of putting your microphones back on. So just make sure you stay muted and you'll enjoy the show. So that's my short and sweet introduction. I'm now going to pass over to Jerry, who's going to introduce tonight's speaker. So Jerry, if you're ready, over to you.
The subject tonight is planetary nebulae. Now, astrophotography is quite a major topic within the society. With our astrophotography group produces some amazing things. If you want to know more about it, then do see Dennis, who's down the front here. He will be happy to tell you about the meetings. If you are a HAG member, then you have free membership of the astrophotography group as well. so you can come along to the meetings without having to pay. Now, there's so much detail about astrophotography that some people specialize in particular areas. And we're going to hear about one particular specialist area from our speaker tonight, Peter Goodhew, who works with, it's a worldwide group, isn't it? Yeah. Effectively, using remote telescopes in various locations. And he's going to talk to us about imaging planetary nebulae. So I'm looking forward to lots of lovely pictures. Thank you.
Thank you for that flattering introduction. Yes, and where do I start? Every month I get a massive kick from doing something that very, very few people ever get to do. And that see something in the universe that has never been seen before. And that's because I'm in this group. We don't just photograph planetary nebulae, we discover them. And so we're a research group. I have the main members are in France, Germany, UK, Sweden, Hong Kong, but there are others also in other countries, Belgium and Spain and California. And it's been a life-changing experience for me. I've been doing this for 2 years. But it also, my journey started 8 years ago when I set up an observatory in my garden at home. I had a 4.5-inch refractor, and I got a camera and started doing photography. It wasn't too long before I realized that there was a lot of light pollution in London. I also realized that I put tall buildings and tall trees all around my garden. And what was worse is that I'm directly under the approach path for the North Runway at Heathrow. So I was trying to do astrophotography from probably the most stupid place on the planet to try and do this. So that drove me to find a better solution, and I set up 2 telescopes in Spain at a dark site. It's in a remote forest, and it's 5 kilometers from this village. There is one light bulb about a kilometer away, but it's only a 40-watt. So it's very, very dark there. And of course, the weather is a lot better. In London, where I live, I have about 280 cloudy nights a year. In Spain, I have about 280 clear nights a year. So that makes quite a difference. Also, there were some other advantages I didn't quite realize at first. It's a much lower latitude. It's over 1,000 miles south from here. So being much lower latitude, you can actually see further into the southern hemisphere. And also, you get darker skies in the summer. On midsummer's night, it's dark for 6 hours, astronomically dark enough to photograph for 6 hours. So with 2 telescopes, I can do 12 hours of photography in midsummer, where in UK, nobody would even bother to try doing that. And I'm talking about deep sky photography here, rather planetary photography or lunar photography, which is more flexible. So with that capacity, I was able to start doing very, very deep imaging. And my interest was planetary nebulae. I think they're incredibly beautiful and attractive. And I could do long exposures. So I started doing more exotic things that are unlikely to have been imaged or wouldn't have been imaged very much. Now, just give you an idea, here's a picture of my twin telescopes. They're both 6-inch refractors. And here you can see them showing off a short clip showing the mount parking the 2 scopes. You get to see both sides of them. And yes, the sky is blue. Now, that's enabled me to do a lot of deep imaging. But earlier this year, in the springtime, I was contacted by a Swedish amateur astronomer. His name is Sven Eklund, and he had just installed a telescope just a few meters away from mine. And this is in this dome. And he contacted me. He said, look, I see all this stuff that you're doing. Is there any chance I could play with you as well and join in? And I welcomed him with open arms. So now we have 3 telescopes working every night. There are 3 telescopes operating right now, all pointing at the same target. So we can now do a lot of imaging with a lot of clear nights and with 3 telescopes. Okay, so let's now talk about planetary nebulae. What are planetary nebulae? Some of you will be familiar, but it's important that we all have a common understanding because it influences a lot of what I do and how you can interpret and understand the work that we do. You know, if we start from the basics, all stars are made out of big balls of hydrogen gas, and under gravity it gets compressed. When it gets compressed enough, you get a nuclear reaction, and the star starts glowing and sending out light. And now that nuclear reaction generates a lot of radiation pressure, and that radiation pressure counteracts the gravitational pull in, and it results in the star being in balance. However, eventually at some point, the hydrogen fuel will run out. And when that happens, the radiation pressure goes down and gravity takes over and the star implodes. If the star is more than 8 times the mass of the sun, that implosion will be very violent and we'll have a supernova. If it's less than 8 times the mass of the sun, then it won't be as violent. But what will happen is that the implosion results in a shell being thrown out, and what is left then compresses into a very small, hot star called a white dwarf. I'm always a bit confused why we call them white dwarfs, because they're always blue, but anyway. Now, that outer shell is then thrown out, and it is the white dwarf gets extremely hot. It will be about 100 times hotter than our sun, and it sends out really intense ultraviolet radiation. That radiation ionizes the shell that's been ejected and makes it glow, and that's what we see when we see a planetary nebula. So a lot of images of planetary nebula, you should see a tiny, tiny blue star right in the middle. It's very small because it's only a part of what the original star was. But it's also small because its gravity is now not, there's nothing stopping gravity, so it pulls it right in, and that's why it gets so hot. Okay, now that outer shell contains a variety of things, but there are 2 elements that send out emissions, light emissions as a result of that radiation. Hydrogen, which will glow red, and oxygen, which will grow a sort of greeny, bluey sort of color. Now, these things are very short-lived. A planetary nebula, it keeps expanding, typically at about 35 kilometers a second. So it gets bigger and bigger and fainter until eventually it disappears and you can no longer find it, and it just gets absorbed into the interstellar medium. Now, 5 to 25,000 years sounds a lot, but when you think, yeah, but our star is what, 4.5 billion years old. So this is really, infinitesimally quick in astronomical terms. The other thing that as it expands, it gets fainter, but as it expands, it also gets further from the white dwarf, so it gets less radiation. That means that the image that we can get of a planetary nebula rapidly gets fainter, both because it dissipates and because it gets further and further from the star. So they're very, very bright at the beginning, they get extremely faint at the end, and then they become, undetectable. Right, let me think. I think that's about, well, yeah, that's it. So here's an example of 4 planetary nebula. A lot of them are spherical, as you would expect from a shell that's been ejected from the star. They can be, different colors, but a fair number usually have some sort of spherical shape, unless something distorts them. And there are others which have very irregular shapes. Here, 4 examples. They, you can barely detect that there was a spherical shell to start with. The distortion occurs because of a variety of reasons, It could be that it's a binary star system and the companion star's gravity has messed things up. It could be that the strong magnetic fields that are affecting things. It could be that there's interstellar medium that it's colliding with, and that will cause distortions, and several other factors. We don't really need to go in right now. But you can see with these examples, the blue-green ones, that's where they're predominantly oxygen that's being illuminated or radiated. And there's very little hydrogen in these examples on the right. And on the left, you've got ones which have got predominantly hydrogen with very little oxygen, so they're predominantly red. And many have a combination of the two. Right, so why do we call them planetary nebulae when they're not planetary? That's a question that often comes up. Well, I'll tell you who I think is to blame for this. The earliest recorded observations, or some of them, were made by Charles Messier, and there are 4 planetary nebulae in his catalogue. He didn't know what a planetary nebula was. He didn't call them planetary nebulae, but we now know, they are what we now know to be planetary nebulae. After him, this young chap, William Herschel, came along, and he made that was Charles Messier. This is William Herschel. 6 years after Messier did his catalogue, Herschel was observing from his garden. It was the year after he discovered Uranus. So, and he was never looking for planets, and in fact, he's famous for the only person to discover a planet for a long, long time. He was just building a very comprehensive catalogue of the sky. Most astronomers at the time were very interested in comets and studying the orbits of comets. I mean, this was only 100 years after we had Newtonian gravity understood, but William Herschel wasn't interested in comets. He was interested in things that stayed still rather than moved. And it was on the 7th. It was 9:30 on the 7th of September in 1782. He was looking up at the sky in the constellation Aquarius, and here are his notes from that evening. I was able to get his notes from the archives of the Royal Astronomical Society. It's a bit difficult to read, but I'll try and read the relevant bit. We can see it's 9:30 o'clock, and he says, "A curious nebula or comet." And he then talked about it being a little oval. And he later on in that night, much later, he went back and had another look at it, and he noticed that it hadn't moved. So he knew it wasn't a comet, so it was a curious nebula. And he'd never seen one of these before. I've produced this image, which is a blurred version of an image I've got of the actual object, to emulate what I think it would have looked like to him visually without the benefit of CCD cameras and all of the things that I get to play with. And you can see that it doesn't look that dissimilar to Uranus, but it's a bit oval. And but also the other interesting thing is he didn't use the term planetary nebula. He just called it a curious nebula. And the term planetary nebula still had not appeared. If we take away the blurring, we can see quite clearly that it's actually the Saturn Nebula. I would have been probably good reason to start calling it a planetary nebula again, I guess. And it's NGC 7009. Now, the term planetary nebula then appeared when he started publishing his very comprehensive catalogues at the Royal Society. Here's one part of one of the catalogues, and we can see that the term planetary nebula now appears. Now, we can't be absolutely certain, but I think I'm pretty confident that it's William Herschel's fault that we call them planetary nebulae, and we still call them the same today, even though they've got nothing to do with planets. Right. So how did I get into doing all of this research? And what happened was that, well, over the last 10, 20 years, amateur astronomers have been doing a lot of discovery of planetary nebulae. They have literally discovered hundreds and hundreds of them. They don't find them by looking through a telescope. Well, we've got the echo back. Right. They don't find them by looking through a telescope. Some of them don't have a telescope. And if they had a telescope, it wouldn't be much use, because if they haven't been discovered until now, that's because they're very, very faint. So what they do is that there are lots of online digital sky surveys produced by space-based telescopes or land-based telescopes, and they're freely available to everybody online. So you don't have to pay for them. And if you study through these, you can look for any faint indicators or clues that there might be something that nobody's found before. So typically there'll be a faint smudge, and it tells you that there's probably something there. You won't know what it is, but if you're part of our group, you're hoping you've come across what turns out to be a planetary nebula. The only way you can find out what it is, because they're so faint, is to take photographs. And that's where I come in, because that's my role within the team. You need very long exposures from a very dark site with no moonlight. And it's only by doing that you can get collect enough photons to find out what it is that's there. Sometimes we find it's a planetary nebula, hopefully. Sometimes we find it's something else. It could be all sorts of things. It could be a supernova remnant. It could be just an emission nebula. And sometimes there's nothing there at all. And in the more extreme case, I've been photographing this thing for 100 hours before we gave up and said, there's nothing to photograph. So it's not for the faint-hearted. Now, I've been taking lots of photographs with long exposures now for a couple of years and publishing them. And some of the researchers noticed this, and they decided to ask for my help in getting some photographs done. I should add that there are a lot of researchers who have found a smudge on a plate and registered it. And 5 years later, they're still waiting for somebody to take a photograph to find out whether there was anything in their smudge. And I get a lot of requests for things which were discovered a long, long time ago, but nobody still knows what's there. So there are two in particular researchers who are the most prolific and most famous, Xavier Strottner in France and Marcel Drexler in Germany. They had independently been making discoveries of planetary nebulae for a while, and 2 years ago they decided to team up together and work jointly. And they just shortly after that, they came up with their first joint discovery, and they contacted me. Marcel contacted me and said, "Would you photograph this for us?" So I was flattered, knowing that Marcel was famous and a hot shot at this. I was very honored to have been invited to work on it. So I took an image, which was the image of their first ever joint discovery. And since then, they've been very busy. They've now made 136 possible discoveries of planetary nebulae, and another 60 odd other discoveries, which turned out not to be planetary nebulae. So about 200 discoveries in 2 years, which I work out is something like one new discovery every 4 days. And that's all through Christmas as well. So they are incredibly successful and very incredibly skilled. So I got drawn into the team, and I've been working not only with them, but with other researchers, but primarily with them almost full time now for the last 2 years. Okay, I'd like to give you a case study of a typical research project that we did. This is, what I should say is, there's a way of cataloging discoveries. If somebody discovers something on their own, we take the first 2 letters of their surname and open a catalog for them. And their first discovery is number 1, second is number 2, and so on. If there are 2 guys working together, then we concatenate their initials. So Strottner and Drexler is STDR. So the first discovery was STDR1. The last planetary nebula is, tonight I'm working on STDR165. But the STDR99 is a useful example. They found this smudge, and I'll show you what it looked like. That's that black smudge at the top there. And this is a survey done by the William Herschel telescope on La Palma. it's in hydrogen alpha wavelengths. Most of these faint images, we invert them because it's easier to see black against a light background and see the other way around. So the sky is always white, and the nebulas are always, or whatever is there is always black. So we can see that there is something. Yeah. So there's a smudge there, not much else. They weren't sure whether this was going to be worth bothering with, and it was really a long time afterwards, only recently, that they discovered that actually there is a white star in the middle, and it's if you look, it's just there, tiny star. Is my cursor working? No, it's not. It was. I lost it anyway. Just up there's a little red cross, and you can see it's a tiny star. When they found that, and it was very, very hot, so that's potentially a white dwarf that could have been at the heart of a planetary nebula. If they don't find one of these, they tend to not bother because it's going to be something else probably. And the problem is that the skies are full of bits of hydrogen gas that could be anything. So you don't go chasing every bit of hydrogen that you can find on a survey. And there are multiple plates here that have been overlaid. So it's looked a bit messy, but that's what the surveys look like. So they asked us to start working on photographing this, and I was doing this only a few weeks ago with my Swedish friend helping. So we did some hydrogen alpha imaging. This is just under 68 hours of exposure, and we can see that smudge at the top has got far more wrapped around it than wasn't visible on the survey. And then we switched to oxygen filters, and this was even fainter. We had to do 119 hours. To be honest, for the first 10 or 20 hours, we didn't think there was anything there. We kept saying, no, there's nothing there, but we persevered. And then if we combine those images together with some stars and do it in color, we end up with this. And that was 196 hours of imaging. But I think it's a very attractive planetary nebula. Now, let me see. I'm going to try and get this cursor. There we are. Oh, it's on my screen. It's not on yours. Go the other way. There we are. Okay. Now, there's some very interesting things about this. First of all, you'll see there's quite a lot. I don't know if it's visible on the screen. There's a lot of background faint nebulosity, red faint nebulosities, hydrogen alpha. The nebula itself, it's not very spherical. It's sort of more ovoid. And the other interesting thing is that it's very, very bright at the top and much fainter at the bottom. And on all the oxygen you can see is at the top. But also, if you look, that there is the original star that the nebulas come from. And it's nowhere near the center of the nebula. And so that's a bit strange, isn't it? Now, let's explain the reason why is that star is moving at very high speed. It's moving from the bottom to the top. So it started off down somewhere around about there. And this nebulosity here was ejected, but it carried on moving forward. And what's happened is that there's a shock wave here because the expanding planetary nebula is colliding with that hydrogen envelope that's all everywhere there, and you're getting a shock wave, a shock front there. And that's why you've got that intensity of brightness. And it's the fact that the star is so high up and so close to this, that tells us that the star is actually moving at an extremely high speed. Normally they don't, but you often do find a nebula will be really, really bright on one side and really, really faint on another. So that's an example of from start to finish as to what we do, and that's when it's successful, rather than 100 hours where you decide that you haven't got anything. All right, how do these discoveries get officially recognized? Well, there's a sort of two-stage process. All amateur discoveries are registered at a site in France, and it's called planetarynebulas.net, And amateur discoveries from all over the world, they get assessed here. The site's managed by a guy called Pascal Ledoux. And if you think you found something, you send it to Pascal and you say, what do you think of this, Pascal? And he'll say, well, look, what have you got to convince me that this is a likely candidate, especially if you haven't got a photograph. So, you have to say, well, there's a hot white dwarf there, and maybe there's a faint smudge. And sometimes you'll say, nah, you're dreaming. And he'll say, it's not worth bothering with. And sometimes you say, yeah, there could be something there. And he'll then register it. So he'll give you a catalog entry with the two initials of your, two letters of your surname and a number, and it's then registered as an amateur discovery. Now, you can't do much then unless we take it further by getting somebody to take an image of it. And the problem is a lot of these discoverers can't find people like me willing to spend all of their money on telescopes to spend all of my time taking photographs for them. And I'm doing it for free, of course. And so there's a shortage of people at Dark Skies with the willingness to sort of take on all this. And there are literally hundreds of discoveries which have been sitting, waiting to be taken any further. And when if you've got a photograph and then you send that to Pascal, then he says, right, now I can see what it looks like. And yet maybe it does look like a planetary nebula. And sometimes he says, now I've got the picture. We know it's not. So you say it's a dud. Then to take it beyond that, we have to get a spectrum of the object to find out what's the chemical composition. And actually, if I go back, here is a good example where you would need to take the spectrum across there, because you've got to position your slit so you get the strongest image, and you get two elements of oxygen and hydrogen, anything else that the spectrum might bring up. But until you know that that's the right place to put the spectrum, it's you could stick it somewhere else and you won't get a useful spectrum. So so it's important to get a spectrum, and again you've got to find somebody willing to do that. And we're lucky there's a network of French astronomers who've got spectroscopic capabilities. And in fact, the French are very good at this, these amateurs. And they've even set up an observatory just for doing spectroscopy down in Chile now. So if you can get the spectrum done, then that will really help us know whether there's any confidence in this being a proper planetary nebula. If you do, then you go to the professionals, and the decisions on planetary nebula being officially recognized are made by an organization called the Laboratory for Space Research at Hong Kong University. And they will confirm and give official recognition if they believe that you've actually found a proper one. The guy who leads it is Professor Quentin Parker. He's the director of the laboratory and a professor of the Department of Physics in Hong Kong. And Quentin is he's recently published an excellent paper. So if any of you want to start doing this crazy stuff, then read this paper. It's Planetary Nebulae and How to Find Them, a Concise Review. And it does describe the process you go through, and it lists some, and also gives you clues as to when you may have a dud. He in the paper that he's just, that was only published in June, he acknowledges the contribution that amateurs are making to the professional community. And here's a quote from the article. It says, the amateur community is making observations that provide unprecedented, high quality, deep imaging, rivaling and in many cases surpassing the best professional images, which is quite flattering to hear that. What's even more flattering for me is he chose two of my images to illustrate that point. Now, the one on the left, I call it Loris Nebula after my partner. And the one on the right, we tried to put names on these. I said to Marcel, it looks like a wine glass. So it's now known as the wine glass nebula because it's got red wine in it and it's got sort of blue glass around the outside. What I was doing now, in terms of time, I asked Marcel Drexler to put together a video for tonight of some of the favorite images that we have discovered over the last 2 years. And it's not just me, there are other astronomers who do photography. There's about a group of up to 10 that take photographs. Some have bigger telescopes, some have wider field telescopes, some have telescopes that are better suited for southern targets rather than northern targets and so on. So you're going to see quite a lot of images that are the result of our work. You'll find that some are possible planetary nebulae, but we're awaiting getting a spectrum produced. Another problem is if by the time you take in all your 196 hours, the object is now so low you can't take a spectrum, you have to wait a whole year for it to come back round. And so a lot will be still pending getting a spectrum. You'll see some which are confirmed because we managed to get a spectrum produced in time. You'll see other objects which are not planetary nebulae. Some are supernova remnants, and some are completely mysterious objects. Even with the help of the best professional astronomers, we can't figure out what it is that we found and photographed. So I'm now going to play this video. I'll try and stay quiet so that you can enjoy it. So take it in. Okay, so every time I look through that, I'm amazed at how much undiscovered beauty there is in the universe. And that's just a small sample of what we've done. And I'm left wondering, what will we find in the next 2 years, or even in the next year? Because there's plenty up there. You saw that one image where there were, I think, 4 planetary nebulae. Actually, there were 8 there. but some of them were very, very tiny. And 7 of them were new discoveries. And that's just in one field of view. So there was, it's an awful lot up there to be found. And we will continue doing all we can. But if anybody wants to buy the beautiful calendar, it will just help us fund some of the rental time that we have to pay out of our own pockets otherwise, for doing all the research we'll be doing over the next year. Right, thank you very much. So now it's over for questions, yeah?
Yes, indeed. We have a few online. Okay. I will.
We can borrow this if you need.
I think you should leave it. I'll shout the question. So Thomas Southern asks, what is the likely dimensions of these objects? And has anyone ever attempted a 3D model?
The dimension, the dimension varies massively. If you think of when a planetary nebula starts, a protoplanetary nebula, as it expands, it's not much bigger than a star. And then as it goes further and further out, it gets bigger and bigger. They can be several arc minutes across, or they can be several arc seconds across. It really, and even several degrees across. So it really just depends on how close it is to us, how bright it remains as it expands, and for how long we can take images of it. What I'll let you into a little secret though. In the calendar, there is something that's not been ever announced, and the people that get the calendar will be the first to know about it. I'm not sure I'm allowed to tell you this amount of detail, but it's half the size of the Andromeda galaxy, and it's right next to the Andromeda galaxy, and nobody's ever seen it. We've only just found it. So if you want to be the first to see it, buy the calendar. The other thing I should say is the orders close on Friday, so you're going to have to be nippy if you do want one.
Can we repeat this question? What is the typical age of an average nebula? That's from Peter Jenkins. Right. So the question is, what is the typical age of an average nebula?
Oh, another tricky one. They don't really, well, there's no point where they die. They expand and expand and they become invisible, but they're still there, but they're so faint you can't find them. Until people like us, crazy people, started doing hundreds of hours of imaging, people assume that all of these had already died and gone away. They just get fainter and fainter and fainter. They do ultimately spread into the interstellar medium, but at what point? I mean, at what point does a sound wave stop? I don't think I can give a sensible answer to that.
One question is, how do you prioritize which objects you investigate further?
Oh, that's an excellent question. At the beginning, I wasn't very good at this, and I get inundated with requests from people who say, "Can you do something for me?" And I still get requests every week. When I wasn't very good, that's when I spent 100 hours just taking a photograph of empty space. You learn to take the techniques to whittle out the good opportunities from the duds. One is, well, who's the requester? Some of the people have amateur researchers, have what I call a vivid optical imagination. And they're convinced that there's something there. And so you take 5 hours, now there's nothing, 10 hours, no, nothing, 30 hours, nothing, 70 hours. Oh, but if only we had a bit more. So you learn that some people have a high probability of giving you a dud. Others, like Marcel, take a lot of care in trying to make sure they don't give you duds, but they still get some duds. One of the key requirements you look for is there a bright white dwarf near the center? That always helps. The other thing is the oxygen emission. If they found it almost certainly on a hydrogen sky survey. So we know there's a hydrogen smudge there. But if you don't have oxygen as well, then it's unlikely to be a planetary nebula. Now, the oxygen might be very, very faint, but if you don't have any oxygen, then it's possible it could be a nebula, but unlikely. And I would not want to spend my time doing one that has no detectable oxygen, because that's when I end up wasting 100 hours or so. So what I normally do is I start off with doing some test imaging using an O3 filter to see if after a few hours we can detect something there, even if it's just very, very faint. If after 5 or 10 hours we can't detect anything, then we'll put it in the out basket and move on to another one. But yeah, so it's a question of track record of the researcher, and then whatever evidence there is to support it being a planetary nebula. And if, for example, you could look at some red, green, blue plates, and if there's a faint blue smudge and a green smudge, then that could imply the presence of oxygen. Mm-hmm. So you look at what is there to make it credible, and then you do some test imaging. And if the tests show that there's something, then you carry on. If they don't, then on to the next.
So with SDDR 99,
yes,
where the star was right
up the top, yeah.
How did you determine which star was the source?
Okay, these stars are, as I think I mentioned earlier, incredibly bright and very hot. Like 1 million times hotter than the sun. So very, very hot, extreme ultraviolet radiation. So one of the markers is there a star somewhere in this field of view which is brutally intense in terms of ultraviolet radiation? And there are ultraviolet surveys that we can use, and to see which stars have got the high enough temperature to be likely to be, and in that case, there was only one.
Yeah, so spectrograph.
Yeah.
What sort of typical distance are we talking about?
Okay, the question is, what sort of distance are we typically talking about? Measuring the distance of planetary nebula is intensely difficult, and in many cases we do not know. Sometimes you can interpolate it. So if you can use spectroscopy to measure the speed of expansion, then you can retrofit and you can say, well, if it's expanding at that much and it started at 0, then you can work back and you can say, well, that's the size of it. It still doesn't necessarily help you about how far it is unless you've got a star embedded within it where you can get the measurement of the star. But in many cases, we just don't know. Where we do know, it's in the calendar, by the way.
Yeah.
So yeah, go on.
Your kit, to be honest. I think you've got these telescopes down in Spain, 190 odd hours. You're here and the kit's there, presumably. Yes. I mean, is it an observatory or?
It's an observatory. Yes, it's running at the moment. I was looking at live just before we started. No, it's in dedicated observatories. You know, I have my own roof. Sven's got his dome, so we control the roof. It's totally robotic. I've got an awful lot of telemetry that comes in constantly, about 8 or 10 thermometers, for example, doing temperature readings with cameras and other bits of equipment. It's all pre-programmable. I set it up before I left London to come here, and it started automatically at 7:30 Spanish time, and it's designed with a lot of resilience. You've got tens of thousands of pounds worth of equipment sitting in a field with nobody for kilometers near it, and the roof is open, and an unforeseen thunderstorm breaks over, and that knocks out the power, and it also knocks out my laptop. And just at that moment, the local farmer, and this has happened many times, he's dug through the fiber optic cable. So you've lost connectivity, and this is at 3 o'clock in the morning, I don't stay awake at night worrying about that. There's battery power. Even with if my laptop crashes, the roof system's got its own automation. It will park the mount if the weather says it's getting bad, or the internet goes down. And then once the mount is parked, the roof will close. So it's pretty fail-safe. Yeah, and I don't worry at all about all of my expensive toys being left in this field with the roof open 1,000 miles away. There's another question.
Yeah, thanks. I wanted to ask you a bit about the technology or technique of your acquisitions in terms of the filters and oxygen and hydrogen filters and stuff. Do you always use the same kind of proportion of time spent through each filter, or does it depend on what you're targeting? And as the target kind of emerges, do you kind of vary it?
Okay, so the question is, how do we decide how much time to spend on each filter when imaging an object? That's an easy question at last. We start off by doing test imaging with the different filters to find out how bright is the hydrogen, how bright is the oxygen. And once we've done some test imaging, we'll see that one is 3 times brighter than the other. The one that we're doing right now, it's very, very bright in oxygen, it's very, very faint in hydrogen. Others will be on the opposite way around. So we do a certain amount of imaging, 50-50. And then once we realize that one's brighter than the other, we'll concentrate more on one. But with three telescopes, we can have 2 telescopes doing hydrogen and 1 telescope doing oxygen at the same time. And then we just keep going until we find that there's enough strong signal data there to process an image and produce an acceptable image.
So would you spend more time on the fainter?
Yes.
Yeah.
Yes. Yeah. We need more. If we need more, the question is, do we spend more time on the fainter one? Yes. We need more photons if it's fainter, so we collect more photons. So we'll in the case of the one I showed you, it was 120 hours of oxygen because that was very faint, and it was, if I remember, about 90 hours or 80 hours of hydrogen. So we did a lot more of the oxygen because that was fainter, and we had to bring in more data to be able to produce an acceptable image.
That leads on nicely to a question from Kevin Noble, who asks, what's the longest imaging that you've done, and how do you decide when you need to stop?
All right, so hi Kevin. The longest one was the one that I've done, was the one that I showed in the talk. So that was 196 hours. When do we decide when to stop? Well, Marcel is, in my view, the best image processor on the planet. He has remarkable skills at producing high quality images from very, very faint signals. And we don't have time to go through all of that, but Marcel's the ultimate arbiter. When we say, he says, I've now got enough data, I can produce a good image, then we stop. But we don't stop until the boss says stop. And so we just keep plowing away. The only exception might be, for example, we're working on 2 targets in Cygnus right now. Cygnus is getting very low, it's getting very late in the season. We're prioritizing those because next month it'll probably be too late to do anything. So if we don't do it now, we'll have to wait a year. So that's one way of prioritizing. And we're trying very hard to just get as much data as we can while we can. But it's up to Marcel to say when we've got enough. And if it's never happened, but in the unlikely case we couldn't get enough, we'd have to wait until it comes around next year.
So nearly 200 hours. If you could do 5 hours a night, we're talking about 40 nights worth just for one object.
Well, except that we've got 3 telescopes.
Yeah.
And in winter, we can do 12 hours a night. And so we can do 36 hours in one night. So
that cuts it down.
So we can do 200 hours in a week easily.
Okay.
Yeah.
Makes it much easier. Right. Yes.
Is it possible to witness Doppler effect with light? Things coming towards and going away?
Well, yes, that's what spectroscopy does. So when I mentioned you can see how much a nebula is expanding by, you can take Doppler image of the back, the far part of it, and the front part, and you can see the Doppler shift there. You can measure the Doppler shift, and that then tells you how much, at what speed, the front and the back are moving apart. So yes, and that's precisely the sort of thing you can only do with spectroscopy.
You mentioned the importance of sighting the telescope in an area where there is no light. And I wondered if any work like this is being done somewhere like South Island, New Zealand, where when I was there, the sky was amazing and there was no light pollution. And if anyone is doing that, are you linked with them at all?
Well, there's nobody doing it in New Zealand or Australia, even though there's some beautiful dark skies there. We are getting some work done in Chile, but again, as I said, we're having to pay for professional telescopes to be used to do that. We haven't got anybody, well, there are very few serious amateur astrophotographers with big scopes in the Southern Hemisphere who are offering to help us. So in fact, there are none. So if anybody knows of somebody who's got a huge telescope at a dark sky location in the Southern Hemisphere and they don't know what to do with it, just tell them to call me, okay? And I'm sure we can keep them very, very busy.
But there's also a reason why the big there for long white clouds. It gets very cloudy down there.
Yeah, and Chile is the best place really in the Southern Hemisphere because you've got dry atmosphere, you've got very clear skies, and you've got very few clouds here.
Any other questions online? One more popped up. Typically, what exposure times do you use for each frame, and what software do you use for stacking and post-processing?
Oh, right. Okay. So, did everybody hear that? Okay. So the question is, what exposures do we use for each frame, and what software do we use for stacking the images? On my 6-inch refractors, I will do narrowband imaging on 15-minute exposures, 900 seconds, and broadband, red, green, blue luminance, I'll do those on 300 seconds, 5 minutes. My buddy Sven, because he's got a much bigger light bucket at 14 inches rather than 6 inches, he captures far more photons, so he even does narrowband imaging on 5-minute exposures. What was the second part of the question?
What do you use?
Oh, how do we stack? Yeah, we use PixInsight for stacking the images, but most of the post-processing is done using Photoshop. Right.
Any more questions in the room? Yes.
Well, a stupid question.
No, there are no
No,
stupid
no.
questions. There are only stupid answers.
Given the time and exposures that you use and the size of the sky, just a rough idea, how long did you feel you needed to carry on this project before you pretty much covered?
I think that man will no longer be on this planet when we get to that point. The thing that is obvious to me from what I've been doing is that there's just so much waiting to be done. I mean, there are hundreds of things that have been found and nobody's yet photographed them. And we're finding things faster than we can photograph them. I've complained to Marcel and Xavier that, can you please slow down in discovering these things? Because, they can find it in 5 minutes and it takes us 200 hours to take the photograph. It's not fair. So there is, I think, no limit to what can be discovered. Ultimately, if we do get close to finding everything, we just have to get bigger telescopes and do longer exposures, and there'll be more stuff that's even fainter than we go after that's waiting to be found. Photoshop.
Do you think the other one out there now?
What do you mean by the other one? Oh, Affinity. I like Affinity. It's I think it's got a long way to go to do some of the things that we do. We probably stress test and use these products more than the average user. So I mean, I think Affinity, certainly on the initial reviews I saw, and I in fact bought it. It seemed very user friendly and very good for people more starting out. I think that, well, I have no say in it anyway, because Marcel does all the post-processing and he's the boss. So, and he's been using, he's a graphic designer as well, so he uses Photoshop professionally. I don't think there's any hope of persuading him to try anything else. Right.
Yes. And the volume of data that you have to ship around, whether it's back to your base.
Yeah.
I mean, what sort of, how many gigabytes to take it to?
Oh God.
200 hours.
Off the cuff, I'm not sure how many gigabytes. Typically, each frame would be typically 23 megabytes, something like that. I use Google Drive. We use Google Drive to automatically download each frame from the camera. We have a high-speed fiber optic link out to Spain. And about within 1 minute of the frame being downloaded from the camera, it appears on this laptop, because I've got Google Drive at both ends, and so Google Drive syncs it. So as soon as it's on the hard drive in Spain, it starts moving through here, and it arrives shortly afterwards. I then package up everything I've got and send it to Sven, because he does the stacking. I send that to him in the morning. I've got a fairly fast broadband connection, but it would take me, say, 10-15 minutes to send it to him. So and then he will then stack it all together with his data, and then it's only the stacked results that we then start sharing. So the heavy shifting is really from the camera to Sven, and then after that it's all stacked, and then it's fairly small volumes. But yeah, we have a lot of hard disks, which are multi-gigabyte hard disks. Yeah, so I think I've got on my 5th hard disk now.
Okay.
Yep.
Right. Well, I said at the beginning that I was looking forward to seeing some nice pictures, but I think you'll agree that what we've seen has been quite staggering. There have been some incredible images and really beautiful images as well. And I'm sure that you really appreciate the incredible amount of work that's gone into producing them. And I've really enjoyed listening to Peter this evening, who has beautifully described his work, and I'm sure you'd all like to show your thanks to him. Thank you. Okay, before I hand back to Alan, I'd just like to mention one thing, which is that this weekend, the Federation of Astronomical Societies, which is the national body that supports all the local societies around the country, is having its 2022 national convention. The theme is Women in Astronomy, and I'm delighted that we have as our keynote speaker, Dr. Jocelyn Bell-Burnell, who found a bit of scruff in the output from the Cambridge Radio Telescope back in 1967, and that turned out to be the first pulsar. We have 3 other speakers. It's only £10 for the whole day. As Jocelyn is based in Oxford, that's where the event is taking place. If you're interested, today is the last possible day to book. Please come and see me after the meeting. I'll give you details of how you can come along. I think that's about it then. So back to Alan. Alan.
Thank you, Jerry. I'd like to say a very special thank you to Peter. That was a fascinating talk about objects which must be very difficult to find in the sky, and the amount of work you put into producing those images and analysing what those structures are made of is absolutely phenomenal. So on behalf of the Hertford Astronomy Group, I'd like to thank you, Peter. just a few more announcements before we disappear. The next meeting of our club is on the 14th of December, when Jerry will give a talk about the last men on the moon for now. Hopefully by that time, the Artemis 1 rocket will be on its way and doing its journey. If you want to watch it live, it's due to go on the 16th of November. You can check the times on the NASA website, who no doubt will be given a live transmission of it. Thank you also for all of you who came to the Bayfordbury Open evening recently. You might be interested to know that the next one is due on December the 2nd. So if you want to come along and help Hertford Astronomy Group, there will be a contact point on the website and you'll be able to join us then. So that's all we have for tonight. I'd like to say thank you ever so much to the technical team down at the university, all of the committee members who worked so tirelessly to make these productions possible. Do have a safe journey home if you're leaving university. And those of you on Zoom, thank you for coming along. I know that you're all over the country as well as in Hertfordshire. It's been a pleasure meeting you, and we look forward to seeing you at our next meeting on December the 14th. Bye for now.